The human eye. It's the lens on our colorful world. With enough light, shape and movement are focused at the retina and transmitted to the brain. But in the dark of night, we lose color. We see the universe in black and white. We miss the light fantastic. It's not that stars lack color. Our eyes lack sensitivity. At such a distance, they can't gather enough light. We're blind to the colors of the cosmos. And we're distracted by our own lights, aircraft, satellites, shops, traffic. The stars were first viewed seriously through a telescope by the Italian Galileo, but he saw no color. His optic tube collected no more light than a pair of modern binoculars. But Galileo opened up the galaxy. He discovered moons around Jupiter. He spotted craters on our moon. He announced that the planets circled the sun. And when he looked at the Milky Way, it was no hazy band of light, but millions upon millions of stars. Three and a half centuries later, in Earth orbit, the Hubble Space Telescope is the optic tube of today. The Hubble didn't discover color, but it sees fine detail as never before. In dazzling clarity, the cosmos is yielding its secrets. The human eye is like a camera. At the front is the lens. The pupil adjusts its aperture to cope with the brightness of the incoming light. It's focused at the retina in the back and passed to the brain. Trouble is, our pupils, at their widest, are still too narrow to see the night sky and color. They gather insufficient light to trigger our color receptors. For that, we need a telescope. This is a refractor. Light is simply gathered through a large lens and magnified in an eyepiece. It's the oldest type of telescope, the design used by Galileo. The refractor's drawback is lens size. Any bigger than 3 feet across, and the lens deforms under its own weight. Big modern telescopes are reflectors. Light is gathered by a mirror. The mirror on this reflector is nearly 14 feet across. The scientist who first demonstrated the reflector was the Englishman, Isaac Newton. A reflector has 2 or more mirrors. The big one is like a bucket collecting light. It can be much bigger than a lens because a mirror is more easily supported. Light entering the reflector first bounces off the big mirror, then off a small mirror, and to a focal point where it's recorded and stored electronically. Rather than squinting through telescopes, today's astronomers analyze computer images and the occasional photograph. What is this fantastic light that astronomers gather? Light is generated when electrons in an atom jump from one orbit to another. They radiate energy. That energy is light. Because stars are so distant, their light takes hundreds, thousands, even millions of years to reach us. And they send us more than visible light. They emit an entire spectrum of radiation. Visible light is at the center. Gamma rays to the left come on the shortest wavelengths, radio waves to the right on the longest. This radio image is the debris of a star that blew up. Another radio image, clouds of gas shooting from a galaxy in distress. With dishes instead of mirrors, radio telescopes work like optical reflectors. Incoming radio waves are bounced to a focal point above each dish. Radio dishes are big because the wavelengths they catch are so much longer than those of visible light. The dishes scan day and night, and in any weather. The Parkes Radio Telescope in Australia, famous for its work on pulsars. Pulsars are tiny, dense stars, only 10 miles across, but they have the mass of our sun. Their pulses are filtered from the background noise of the cosmos and from terrestrial sources like microwaves and car ignitions. Only now does a pulse from the star peak out, one beat from a pulsar spinning many times a second. In this display, the astronomers have two pulsars in their sights. They're the relics of gigantic stars that exploded as supernovas, stellar corpses condemned to an afterlife of beaming radio peeps from the heavens. More pictures by radio. We're looking at matter hurtling from a region near a black hole. There it goes again. Here's what's happening. The black hole is stripping a star of its gas. As the gas whirls toward oblivion, there's a twin expulsion, a sort of cosmic belch. When radio telescopes hook up to scan in unison, their images are rich in detail. That's how they work in New Mexico at the VLA, the Very Large Array. 27 dishes on a Y-shaped railroad covering up to 500 square miles. They turn like flowers and track like streetcars. Together, they probe the cosmos with the scope of a single dish 17 miles wide. And when they link with this dish in Hawaii and another in Puerto Rico, they form a telescope thousands of miles across. Linked globally, they make a dish the size of the world, a telescope so powerful it sees back to a time before there was life on Earth. The telescopes of several nations perch on a volcanic peak in Hawaii. At over 14,000 feet, they're halfway up through the atmosphere. Here, clear of clouds and the water vapor that absorbs it, infrared radiation is collected. Infrared reveals heat. It sees through dust to find stars and into dark clouds where stars are born. Shrouded in dust, here's part of our galaxy in visible light. The same region in infrared. Infrared is so close to visible light that images look optical. They take us to the core of the Milky Way, invisible to optical telescopes. The planet Venus is perpetually veiled in clouds. Infrared reveals a hint of surface features. Infrared radiation was discovered in England by the astronomer William Herschel. Herschel was famous for discovering the planet Uranus, and almost as famous for his telescopes. The biggest had a mirror 4 feet across. Even so, it glimpsed Uranus only as a spot. Uranus didn't look much better through telescopes until these pictures in 1994 from the Hubble Space Telescope. They show cloud formations. And for the first time in an optical telescope, Hubble pictured the rings of Uranus. Herschel thought he saw holes in the sky. He was mistaken. They're Bach globules, clouds of black dust that float in front of these stars. Nevertheless, Herschel was a remarkable observer. He compiled a star map of the heavens, with the sun at the center. In Ireland, telescope building grew bigger and better. In 1845, the 3rd Earl of Rosse built this monster with a 6-foot mirror on the grounds of his castle. For 3/4 of a century, it was the world's largest telescope. Night after night, Lord Rosse tracked objects in the sky. He viewed them through an eyepiece and put them on paper. His sketch of the Great Nebula in Orion. The same region in a modern photograph. His drawing of the Crab Nebula. The modern picture. Rosse gave the Crab Nebula its name. It's the remnants of a giant star that was seen to explode 950 years ago. In this brilliant image, the Hubble telescope identifies the pulsar that remains at the center. Cloudy Ireland isn't the best place for stargazing, but Rosse persevered. His telescope was dubbed the Leviathan of Parsonstown. These are his drawings of what was known as a spiral nebula. Today, it's identified as a galaxy, the Whirlpool. The Whirlpool has been interacting with a smaller galaxy for hundreds of millions of years. Here, in computer animation, stars and gas trail into space. They look close, but the galaxies are between 10 and 15,000 light-years apart. Billions of stars in a game of cat and mouse. Hubble has peered deep into the Whirlpool. Part of the dark shape at the center may be a vast ring of dust circling a black hole. By the early 20th century, telescopes were enormous. This one, the Hooker reflector, was completed in 1917. To take advantage of dark skies and clear air, it was sighted on Mount Wilson, near Pasadena, California. Astronomers hadn't reckoned on the spread of Los Angeles. The Hooker was the first truly modern instrument. Its mirror is 100 inches across. To keep it on target, electric motors drive a tracking device to compensate for the Earth's movement. It's built big and moves like a dream. Gone were the uncomfortable vigils of Herschel and Ross. The astronomer George Hale, who designed the Hooker, enclosed both telescope and observer. From this mountaintop, fundamental discoveries were made, and modern astronomy came of age. The 100-inch reflector on Mount Wilson revealed our position in space. We're not at the center of things. The sun is in the outer reaches of a huge disk of stars, a spiral that bulges at the middle. A galaxy we call the Milky Way. But is our galaxy the entire universe? The Mount Wilson observers decided not, and one astronomer discovered why. He was Edwin Hubble, after whom the Space Telescope is named. In 1923, Hubble made a blockbuster of a measurement through the Mount Wilson telescope. He was observing Cepheid variables in this fuzzy patch of sky, stars that brighten and fade and are a key to working out distances. They were so far away that Hubble realized he was looking at another galaxy, more than 2 million light-years away. Hubble had identified Andromeda, one of the closest galaxies to our own, and he found more and more galaxies. He thought the shape of galaxies indicated their evolution. They began as formless aggregations that became increasingly tightly wound. They developed arms, he believed, that grew and wrapped up the galaxy like a ball of string. Hubble was wrong. Different galaxies have different shapes, whatever their age. But he was right on a basic truth of the cosmos. Hubble showed that galaxies everywhere are moving apart. He'd hit upon the expansion of the universe and the notion that it all began with a big bang. In 1948, Edwin Hubble became director of the world's largest telescope, the 200-inch Hale reflector at Mount Palomar, California. But Hubble was at the end of his career. Later, he was to be credited with the most significant contribution to cosmology since the time of Copernicus. 4 centuries earlier, Copernicus suggested the planets orbit the sun. As Hubble handed the torch to younger astronomers, a worldwide boom in telescope construction was on the way. The sky seemed the limit. At Kitt Peak in Arizona, there mushroomed the largest collection of telescopes in North America. It's an ideal location for astronomy, high enough to lose the distortions of the lower atmosphere, remote enough to avoid air and light pollution, dry enough to observe almost every night. Where better to gather the light fantastic? In the Andes, perhaps. At La Silla in Chile is the European Southern Observatory. Off Africa, on a volcanic peak in the Canary Islands, Britain's William Herschel telescope is one of a group. And above the clouds on Mauna Kea, Hawaii, sits the very latest. The domes of the Keck telescopes, cosmic binoculars. Keck is like twin cathedrals. It's the biggest telescope in the world. Two mirrors, each twice the width of the huge Palomar reflector, link electronically. More than 30 feet across and made like a jigsaw puzzle, they comprise 32 hexagonal segments of glass. Each segment is controlled by computer. They're moved and flexed in a fraction of a second. This way, they compensate for image distortion caused by the atmosphere or by any change in position of the telescope. Keck is still being tested, but it's already delivering results. Like this superb image of the Eskimo Nebula. And this spiral galaxy. The Hubble Space Telescope. Astronauts at work. Clear of Earth's atmosphere, Hubble was meant to be the finest eye on the heavens in the history of astronomy. But it wasn't. The main mirror had been made too shallow, and Hubble's first pictures were out of focus. The solution was the Great Hubble Fix. The space shuttle was sent up. Its mission to fit the defective mirror with glasses, simple on Earth, tricky in space. But they did it. Hubble was set adrift to resume observation. From Earth, astronomers tested the new lenses. They worked. Since 1994, Hubble's images have gratified us, amazed us, stunned us. They've caused astronomers to look anew at old theories, even the age of the universe. In our quest for the light fantastic, Galileo's optic tube was the first great leap. Hubble may well be the second, and even greater one.